Listening practice, detailed breakdown of Chapter 1, overview of water resources engineering, including subtopics, key concepts, and real-world applications. Chapter 1, overview of water resources engineering 1.1 Importance of water resources, water as a vital resource, human needs, drinking, sanitation, agriculture, industrial and energy production, cooling, hydropower, ecological balance, wetlands, aquatic ecosystems. Economic significance, agriculture, 70% of global freshwater use. Water scarcity's impact on GDP. Case studies, arid regions, e.g., Cape Town's Day Zero. Transboundary water conflicts, Nile River, Indus Treaty. 1.2 Historical development, ancient systems, Roman aqueducts, qanats, Persia, step wells, India. Industrial Revolution, emergence of hydraulic engineering, Darcy, Reynolds. Sanitation reforms, London's Great Stink. Modern era, Hoover Dam, China's South-North Water Transfer Project. Computer modeling, HEC-RAS, SWMM. 1.3 Global water challenges, scarcity and inequality, 2.2 billion people lack safe drinking water, WHO. Groundwater depletion, Ogallala Aquifer, India's Punjab. Pollution, microplastics, PFAS, agricultural runoff, dead zones. Climate change effects, altered precipitation patterns, floods/droughts. Glacial melt, Himalayan water towers. 1.4 Sustainable water management, principles, integrated water resources management, IWRM. Circular economy, water reuse, zero liquid discharge. Technologies, smart meters, AI-driven leak detection. Nature-based solutions, rain gardens, sponge cities. Policy frameworks, UN Sustainable Development Goal 6, SDG 6. EU Water Framework Directive. Key features for the chapter, boxed examples, Singapore's NE Water, water recycling success. California's Sustainable Groundwater Management Act, SGMA. Discussion questions, how can ancient water systems inspire modern solutions? Is desalination a sustainable fix for water scarcity? Visual aids, infographic, global water stress hotspots. Timeline, milestones in water engineering. Would you like to add a section on ethics, e.g., water rights, or expand on climate resilience strategies? Chapter 2, Hydrologic Cycle and Water Balance 2.1 Components of the hydrologic cycle, key processes, evaporation, oceans, lakes, soil, condensation, precipitation, runoff, infiltration, groundwater flow, transpiration. Storages and fluxes, atmospheric water, surface water, groundwater, cryosphere, glaciers. Residence times, e.g., groundwater versus river water. Global versus local scales, how urbanization alters local hydrology, impervious surfaces. Diagrams and models, simplified versus complex hydrological models, e.g., Penman-Monteith equation. 2.2 Precipitation, evaporation, and infiltration, precipitation, types, convective, orographic, frontal. Measurement, rain gauges, radar, satellite data. Evaporation and transpiration, factors, temperature, humidity, wind. Evapotranspiration, ET, estimation, lysimeters, remote sensing. Infiltration, soil properties, porosity, hydraulic conductivity. Horton's equation versus Green AMP model. Urban impacts, reduced infiltration due to paving. 2.3 Water budget equation, basic equation, \text input, \text output equals \delta \text storage where, input equals precipitation, \p plus inflow, \I output equals evapotranspiration, backslash, et backslash, plus runoff, backslash, r backslash, plus outflow, backslash, o backslash, backslash, backslash delta s backslash, equals change in groundwater slash surface storage. Applications, watershed scale water balance, e.g., Mississippi Basin. Agricultural water management, irrigation scheduling. Case study, Aral Sea disaster, water budget imbalance due to diversion. 2.4 Climate change impacts, observed changes, intensified water cycle, more extreme drought/floods. Shifts in snowmelt timing, affecting reservoir operations. Future projections, reduced runoff in Mediterranean, increased in high latitudes. Saltwater intrusion in coastal aquifers, sea level rise. Adaptation strategies, resilient infrastructure, sponge cities, green roofs. Dynamic water allocation policies. Chapter features, worked example, calculating water budget for a small lake. Discussion topics, how does deforestation alter the water balance? Can cloud seeding mitigate drought? Visual tools, hydrologic cycle animation. Global maps of ET trends, MODIS data. Would you like to add a section on human interventions, e.g., dams, land use change, or expand on groundwater climate interactions? Chapter 3, Precipitation and Rainfall Analysis 3.1 Types of precipitation, mechanisms of formation, convective precipitation, localized, high-intensity storms, common in tropics. Orographic precipitation, mountain-induced rainfall, windward versus leeward effects. Frontal precipitation, warm/cold air mass collisions, e.g., cyclonic rainfall. Forms of precipitation, rain, snow, sleet, hail, drizzle. Monsoonal systems, seasonal shifts in wind patterns. Global distribution, ITCZ, intertropical convergence zone, desert climates, polar regions. 3.2 Rainfall measurement techniques, ground-based methods, non-recording gauges, standard rain gauge, manual measurement. Recording gauges, tipping bucket, weighing type, optical disdrometers. Remote sensing, weather radar, reflectivity rainfall rate, NEXRAD. Satellite estimates, GPM, TRMM missions. Accuracy and errors, wind effects, evaporation losses, spatial variability. Case study, flood prediction using real-time radar rainfall data. 3.3 Intensity Duration Frequency, IDF, curves, definition and purpose, relates rainfall intensity, duration, and return period for design storms. Derivation methods, historical data analysis, Gumbel, log Pearson type 3 distributions. Empirical equations, e.g., Sherman, Talbot formulas. Applications, urban drainage design, culverts, storm sewers. Small dam spillway sizing. Climate change adjustments, non-stationarity in IDF curves, updated NOAA Atlas 14. 3.4 Design storm estimation, approaches, synthetic storms, SCS type I4, US, Chicago hydrograph. Probabilistic storms, Monte Carlo simulation for risk assessment. Temporal patterns, block storms versus alternating storms for flood modeling. Case examples, 100-year storm event for highway drainage. PMP, probable maximum precipitation, for dam safety. Chapter enhancements, worked problems, converting point rainfall to aerial estimates, Thiessen polygons. Developing IDF curves from raw data. Discussion questions, how does urbanization affect IDF relationships? Should stormwater standards be revised for climate change? Visual aids, comparative IDF curves for different climates. Hydrograph animation for different storm types. Would you like to add a section on extreme value analysis, e.g., GEV distribution, or expand on radar rainfall correction techniques? Chapter 4, Runoff and stream flow. 4.1 Factors affecting runoff: meteorological factors, rainfall intensity and duration, antecedent moisture conditions, AMC, temperature, snowmelt contribution, watershed characteristics, slope and topography, steepness, drainage density, soil type, infiltration capacity, hydraulic conductivity, land use, urban versus forested, impervious surfaces, human influences, urbanization, increased runoff coefficient, agricultural practices, tillage, drainage systems. 4.2 Rational method, basic equation, \q equals c dot I dot a q equals peak runoff, m superscript 3 s or cfs, c equals runoff coefficient, dimensionless, tables for land use, I equals rainfall intensity, mm/hr or in/hr, a equals drainage area, hot or acres, assumptions and limitations, steady rainfall over uniform basin, only for small catchments, 200 acres, example application, calculating peak flow for parking lot drainage. 4.3 SCS curve number method. Concept, empirical model relating land use, soil type, and AMC to runoff. Key equation, \q equals \frac, p, 0.2 s, 2p plus 0.8 s q equals runoff depth, mm or in, p equals rainfall depth, mm or in, s equals potential max retention, s equals frac 1000 cn, 10 cn equals curve number, tabulated values, applications, rural/agricultural watersheds, stormwater management in developing areas. 4.4 Hydrograph analysis, components of hydrograph, rising limb, peak, recession limb, base flow. Unit hydrograph theory, linear response of watershed to 1 unit rainfall, convolution method for complex storms, flood routing, Muskingum method for channel routing, reservoir routing, modified pools method, case study, analyzing 2010 Nashville flood event. Chapter features, worked examples, calculating CN for mixed land use watershed, deriving unit hydrograph from streamflow data, discussion topics, how does climate change affect hydrograph shapes? Limitations of the rational method in urban planning, visual aids, comparative hydrographs for different storm events, 3D watershed model showing runoff generation. Would you like to add a section on distributed hydrological models, e.g., SWOT, or expand on real-time flood forecasting techniques? Chapter 5, Groundwater Hydrology. 5.1 Aquifer Properties, Aquifer Types, Unconfined aquifer, water table as upper boundary, confined aquifer, bounded by impermeable layers, artesian conditions, perched aquifer, localized water table above main aquifer, hydraulic parameters, porosity, and void space fraction, sand versus clay, permeability, k ease of flow through material, specific yield, s_y drainable water volume, storativity, s water released from storage pore. Unit head drop, case example, Ogallala Aquifer, High Plains, USA, recharge versus extraction rates. 5.2 Darcy's Law and flow nets, Darcy's Law, q equals ka frac dhdl q equals discharge, m superscript 3 s, k equals hydraulic conductivity, m s, a equals cross-sectional area, m superscript 2, frac dhdl equals hydraulic gradient, flow nets, graphical representation of equipotential lines and flow lines, applications, dam seepage analysis, contaminant plume prediction, limitations, assumes laminar flow, valid for most groundwater systems. 5.3 Well hydraulics, steady state flow, theme equation \q equals \frac 2 pi kb, h_2 h_1, ln, r_2/r_1, \b equals aquifer thickness, h equals piezometric head, r equals radial distance from well. Transient flow, this equation, accounts for time-dependent drawdown, uses well function \w, u, pumping test analysis, step drawdown tests for well efficiency, slug tests for hydraulic conductivity, case study, overpumping in India's Punjab region. 5.4 Contamination and remediation, contaminant types, point sources, leaking tanks, landfills, non-point sources, agricultural runoff, nitrates, pesticides, transport mechanisms, advection, dispersion, diffusion, sorption, remediation technologies, pump and treat, extraction and surface treatment, in situ methods, permeable reactive barriers, PRBs, bioremediation, enhanced natural degradation, monitoring, piezometer networks, geophysical methods, regulatory framework. EPA's CERCLA, Superfund, Program-Chapter features, worked examples, calculating drawdown using this equation, designing a capture zone for remediation well, discussion topics, can artificial recharge solve groundwater depletion? Ethics of groundwater mining in arid regions, visual aids, 3D aquifer models showing cone of depression, contaminant plume animation. Would you like to add a section on saltwater intrusion or expand on emerging remediation technologies like nanoremediation? This chapter provides both theoretical foundations and practical applications, crucial for water resources engineers dealing with subsurface systems. The inclusion of case studies and worked problems bridges classroom learning with real-world challenges. Chapter 6, Open Channel Flow. 6.1 Uniform and Non-Uniform Flow, Uniform Flow Fundamentals, Definition, Constant Depth, Velocity and Cross-Section along channel, Energy Balance, Gravity Force equals Frictional Resistance, Applications, Prismatic Channels, e.g., irrigation canals, Non-Uniform Flow Analysis, Gradually Varied Flow, GVF Backwater Curves, Rapidly Varied Flow, RVF Hydraulic Jumps, Weir Flows, Standard Step Method for Water Surface Profiles, Flow Classification, Subcritical. FR1, Critical, FR equals 1, Supercritical, FR1, Fruit Number Significance in Flow Behavior. 6.2 Manning's Equation, Basic Formulation \V equals \frac 1 nr 2/3 s1/2 q equals \frac 1 nar 2/3 s1/2 v equals velocity m/s n equals Manning's roughness coefficient r equals hydraulic radius a/p s equals energy slope. Practical applications, design of stable channels, tractive force method, flood capacity estimation, composite roughness handling, limitations, valid. For turbulent flow only, accuracy dependent on proper end selection. 6.3 Hydraulic jump, energy dissipation mechanism, supercritical to subcritical transition, applications, spillway stilling basins, jump characteristics, sequent depth ratio calculation, energy loss estimation, classification, weak to strong jumps, design considerations, stilling basin length requirements, baffle block arrangements. 6.4 Design of canals and drainage systems, canal design principles, alignment, selection, side slope stability, freeboard requirements, drainage system components, subsurface drains, open ditches, culvert integration, sustainability aspects, lined versus unlined channels, environmental flow considerations. Chapter features, worked examples, Manning's equation for trapezoidal channel, hydraulic jump calculations, case studies, Panama Canal water-saving basins, Netherlands drainage systems, visual aids, backwater curve profiles, hydraulic jump visualization. Would you like to add a section on computational modeling, HEC-RAS applications, or expand on erosion control methods? This chapter provides comprehensive coverage from fundamental theory to practical design, essential for water infrastructure projects. The inclusion of modern applications and sustainability considerations makes it particularly relevant for contemporary engineering challenges. Chapter 7, Pipe Flow and Hydraulic Networks. 7.1 Energy and Head Loss, Energy Equation Fundamentals, Bernoulli's Equation for Pressurized Systems, Hydraulic Grade Line, HGL, and Energy Grade Line, EGL, Major versus Minor Losses, Friction and Local Losses, Head Loss Calculations, Friction Loss Dependence on Flow Regime, Laminar/Turbulent, Moody Diagram Application, Equivalent Pipe Length Method for Minor Losses, Practical Implications, System Capacity Analysis, Air Pocket Problems and Solutions, Water Hammer Prevention Strategies. 7.2 Hazen-Williams and Darcy-Weisbach Equations, Hazen-Williams equation \V equals 0.849 cr 0.63 s 0.54 \, Empirical Approach for Water Systems, see factor tables for different pipe materials, limitations, water only, turbulent flow, Darcy-Weisbach equation \H_F equals F \frac LD \frac V2 2 grams \, Theoretical basis for all fluids, friction factor determination, Colebrook-White equation, comparison of methods for engineering practice. 7.3 Pump systems and design, pump fundamentals, centrifugal versus positive displacement pumps, pump curves and system curves, net positive suction head, NPSH, requirements, design considerations, parallel and series pump arrangements, variable speed drive applications, energy efficiency optimization, operation and maintenance, cavitation prevention, pump selection for distribution systems, SCADA system integration. 7.4 Water distribution networks, network components, pipes, valves, storage tanks, and fittings, demand pattern analysis, fire flow requirements, analysis methods, Hardy-Cross method for manual calculations, EpiNet software applications, transient analysis needs, design principles, loop versus branched systems, pressure zone management, water age and quality considerations. Chapter features, worked examples, pipe sizing using both head loss equations, pump selection for given system requirements, network balancing using Hardy-Cross method, case studies, major city water supply system analysis, pump station failure investigation, visual aids, interactive pump curve diagrams, 3D network modeling examples, practical applications, field measurement techniques, leak detection methods, energy audit procedures. This chapter provides comprehensive coverage of pressurized flow systems, combining theoretical foundations with practical design methodologies. The inclusion of modern computational tools and real-world case studies prepares students for professional practice in water systems engineering. Would you like to expand on smart water network technologies or include advanced transient analysis methods? Chapter 8, Hydraulic Structures. 8.1 Dams and Spillways, Dam Classification and Design, Types, Gravity, Arch, Embankment, Earthfill/Rockfill, Key Components, Foundation, Core, Abutments, Drainage, Safety Considerations, Seismic Design, Overtopping Protection, Spillway Systems, Types, OG, Chute, Siphon, Labyrinth, Design Criteria, PMF, Probable Maximum Flood, Routing, Energy Dissipation, Stilling Basins, Flip Buckets, Case Studies, 3 Gorges Dam, China, World's Largest Hydro Project, Oroville Dam Crisis, 2017, Spillway Failure Analysis. 8.2 Weirs and Flumes, Weir Hydraulics, Types, Sharp-Crested, Broad-Crested, V-notch, compound, discharge equations, \q equals C_DLH3 halves \quad text, rectangular where, applications, flow measurement, water level control, flume systems, types, partial, Palmer bolus, HS/H flumes, advantages, minimal head loss, self-cleaning, installation guidelines, approach flow conditions 8.3 culverts and drop structures, culvert. Design, hydraulic analysis, inlet/outlet control regimes, shape selection, box, circular, arch, pipe arch, fish passage considerations, modern design requirements, drop structures, types, vertical, baffled chute, step spillway, energy management, hydraulic jump formation control, urban applications, stormwater management systems 8.4 river training works, erosion control, structural methods, groins, revetments, gabions, bioengineering, vegetated bank protection, channel stabilization, meander management, cutoffs versus preservation, sediment control, check dams, vortex settlers, floodway systems, bypass channels, Sacramento River example, levee design, USAS standards, failure mechanisms chapter features, design exercises, spillway capacity calculations, culvert sizing using High-8 software, weir rating curve development, failure analysis, 1976 Teton Dam collapse, 1993 Midwest flood levee breaches, innovation focus, nature like fishways, smart dam monitoring systems, regulatory framework, FEMA dam safety guidelines, Clean Water Act Section 404. This chapter bridges theoretical hydraulics with practical infrastructure design, emphasizing both traditional approaches and emerging sustainable technologies. Would you like to expand on dam risk assessment methodologies or include case studies of international megaprojects? The content prepares engineers for critical infrastructure challenges while addressing environmental and safety imperatives. Chapter 9, Water Demand and Supply 9.1 Urban and Agricultural Water Use, Urban Water Demand, Per Capita Consumption, Residential, Commercial, Industrial Breakdown, Demand Forecasting, Time Series Analysis, Climate-Adjusted Projections, Peak Factors, Diurnal and Seasonal Patterns, Case Study, Cape Town's Day Zero Crisis Response, Agricultural Water Requirements, Crop Water Needs, ET-Based Calculations, FAO Penman Monteith, Irrigation Efficiency, Traditional versus Precision Methods. DRIP, Center Pivot, Soil Moisture Monitoring Technologies, Global Hotspots, India's groundwater depletion in Punjab, Central Valley, California, Aquifer Subsidence 9.2 Water Conservation Strategies, Urban Conservation, Technology, Smart Metering with AI Leak Detection, Grey Water Recycling Systems, Policy Tools, Tiered Pricing Structures, Xeriscaping Ordinances, Agricultural Innovations, Water Saving Techniques, Deficit Irrigation Scheduling, Soil Health Improvement, Cover Crops, Biocar, System Modernization, Lined Canals with Automated Gates, Solar-Powered Drip Systems, Behavioral Aspects, Public Awareness Campaigns, Water Footprint Labeling 9.3 Integrated Water Resources Management, IWRM, Implementation Framework, Key Principles, Basin Scale Approach, Stakeholder Participation, Economic Instruments, Institutional Models, River Basin Organizations, Murray-Darling Basin Authority, Public-Private Partnerships, Decision Support Tools, Criteria Analysis, Water Allocation Optimization, Trade-off Evaluation, Agriculture versus Ecosystems, Digital Platforms, Real-Time Water Accounting Systems, Global Case Examples, Success Story, Singapore's NE Water Integration, Challenge, Colorado River Compact Renegotiation Chapter Features, Interactive Elements, Water Budget Calculator for Urban Areas, Irrigation Scheduling Simulation, Debate Topics, Should Virtual Water Trade be Regulated, Privatization versus Public Water? Management, emerging trends, blockchain for water rights management, AI-driven demand prediction models, regulatory spotlight, EU Water Framework Directive implementation, California Sustainable Groundwater Management Act, SGMA. This chapter equips readers with both technical tools and policy perspectives, addressing water management from individual actions to transboundary governance. Would you like to add a section on climate-resilient infrastructure or expand on indigenous water knowledge systems? The content emphasizes practical solutions for 21st-century water challenges while maintaining scientific rigor. Chapter 10, Reservoir and Watershed Management 10.1 Reservoir Sizing and Operation, Capacity Determination, Mass Curve Analysis, Inflow-Outflow Balancing for Drought Periods, Yield Reliability Relationships, Rule Curves, Seasonal Operation Guidelines, Flood Control versus Conservation Storage Trade-offs, Optimization Techniques, Linear Programming, Multi-Objective Allocation, Irrigation, Hydropower, Ecology, Dynamic Simulation, HECRESIM Applications, Climate Adaptation, Inflow. Scenario Analysis, Downscale GCM Projections, Flexible Operations, Sediment Sluicing Strategies 10.2 Sedimentation Control, Process Fundamentals, Sediment Yield Estimation, USL/RUSL for Watershed Erosion, Sediment Delivery Ratios, Deposition Patterns, Delta Formation Dynamics, Mitigation Strategies, Structural Measures, Check Dams, Off-Stream Settling Basins, Operational Methods, Drawdown Flushing, Turbidity Current Venting, Case Examples, Successful Management. Sanmengxia Dam, China, Retrofits, Ongoing Challenge, Tarbala Reservoir, Pakistan, Capacity Loss 10.3 Watershed Modeling, Model Selection Framework, Lumped versus Distributed, HEC-HMS versus SWOT Comparison, Data Requirements, DEM Resolution Needs, Land Use Change Incorporation, Advanced Applications, Climate Impact Studies, SWOT Mod Flow Coupled Simulations, Ecosystem Services Valuation, Invest Water Yield Modeling, Decision Support Integration, Real-Time Forecasting, Machine Learning Hybrids, Stakeholder Visualization Tools, 3D Scenario Explorers - Chapter Enhancements, Design Workshop, Reservoir Sizing Spreadsheet Tool, Sediment Routing Hands-on Exercise, Critical Analysis, Debate, Should all reservoirs have sediment bypass systems? Ethics Discussion, Upstream versus Downstream Rights in Watershed Management, Emerging Technologies, Satellite-Based Sedimentation Monitoring, Sentinel-2 Applications, Digital Twin Systems for Dam Operations, Global Perspectives, Transboundary Reservoir Conflicts, Nile River GERD Project, UNEP Sediment Management Guidelines. This chapter bridges engineering design, environmental science, and policy implementation, providing both quantitative tools and holistic management perspectives. Would you like to add a section on dam removal case studies or expand on citizen science monitoring approaches? The content prepares professionals for the complex trade-offs in modern water resources stewardship. Feature suggestion, interactive module showing 50-year sedimentation impacts under different management scenarios. Chapter 11, Flood Risk Management 11.1 Floodplain Analysis, Hydrologic and Hydraulic Modeling, Flood Frequency Analysis, Extreme Value Distributions, Gumbel, Log Pearson 3, Historical Flood Marks versus Paleoflood Data, 2D Flood Modeling, HEC-RAS 2D, Mike Flood Applications, High-Resolution LiDAR Terrain Processing, Risk Mapping Techniques, Firm Development, U.S. FEMA Flood Zone Delineation Standards, Climate-Adjusted Recurrence Intervals, Vulnerability Assessment, Building Stock Classification, HAGIS Methodology, Emerging Approaches, Machine Learning Predictions, Real-Time Flood Forecasting Hybrids, Crowdsourced Data, Social Media Flood Reporting Validation 11.2 Flood Routing Methods, Channel Routing, Hydrologic Methods, Muskingum-Kunj Variable Parameter Approach, Hydraulic Methods, St. Venant Equations, 1D/2D Solutions, Reservoir Routing, Modified Pools Method, Storage indication curve applications, emergency spillway analysis, breach. Formation modeling, HEC-RAS dam break, urban system routing, SWMM modeling, green infrastructure performance assessment, underground network interactions, storm drain capacity coupling 11.3 structural versus non-structural measures, structural solutions, levee systems, USAS reliability-based design, overtopping protection, armored crests, flood walls, urban space-constrained applications, detention basins, multi-stage outlet designs, non-structural strategies, floodplain. Regulations, conditional letter of map revision, CLOMR, process, warning systems, IoT sensor networks with automated alerts, insurance programs, risk rating 2.0, NFIP updates, hybrid approaches, room for river, Netherlands, controlled floodplain expansion, Sponge City, China, permeable pavement integration - chapter features, case study deep dives, 2021 European floods, modeling versus reality, Houston's post-Harvey floodplain buyout program, interactive components, flood damage calculator, structure type times depth, levee breach simulation sandbox, professional standards, ASCE 24, flood resistant design, EU floods directive implementation, future challenges, compound flooding, rain surge interactions, equity in flood protection investments. This chapter provides actionable methodologies for flood risk reduction while confronting climate change uncertainties and social justice dimensions. Would you like to expand on nature-based solutions or include a cost-benefit analysis framework for mitigation alternatives? New feature proposal, augmented reality tool visualizing flood depths on user's street under different scenarios. Chapter 12, Water Quality Engineering 12.1 Physico-chemical parameters, key water quality indicators, physical parameters, turbidity, temperature, color, and conductivity, total suspended solids, TSS, versus total dissolved solids, TDS, chemical parameters, pH, dissolved oxygen, DO, biochemical oxygen demand, BOD, nutrients, nitrogen, phosphorus, and heavy metals, lead, arsenic, emerging contaminants, PFAS, microplastics, pharmaceutical residues, measurement techniques, field methods, YSI multi-parameter probes, spectrophotometry, laboratory analysis, ICP-MS for metals, GCMS for organics, real-time monitoring, sensor networks with IoT integration. 12.2 Pollution sources and control, point source pollution, industrial discharges, NPDES permit system, USA, zero liquid discharge, ZLD, technologies, municipal wastewater, combined sewer overflows, CSOs, mitigation, non-point source pollution, agricultural runoff, best management practices, BMPs. Buffer strips, constructed wetlands, urban stormwater, low-impact development, LID, techniques, pollution prevention frameworks, source reduction, green chemistry in industry, treatment trains, sequential barrier approach. 12.3 Water treatment basics, conventional treatment processes, coagulation/flocculation, jar testing optimization, sedimentation, tube/plate settler designs, filtration, rapid sand versus membrane comparisons, advanced treatment options, disinfection. Alternatives, UV, ozone, chlorine dioxide, adsorption technologies, activated carbon, biocar applications, emerging solutions, decentralized systems, household water treatment, HWT, in developing countries, nature-based systems, biofiltration, phytoremediation. Chapter features, interactive learning tools, virtual water quality lab experiments, treatment plant design simulator, case studies, success story, Rhine River cleanup, from dead river to recovery, ongoing. Challenge, Ganges River pollution abatement, professional practice, WQI, Water Quality Index, calculation workshop, regulatory compliance scenario analysis, future directions, AI-powered anomaly detection in water quality data, circular water economy applications. This chapter bridges fundamental science with engineering applications, preparing students for both technical design and policy implementation challenges. Would you like to expand on industrial wastewater specifics or include a section on water quality modeling, QUAL2K applications? New feature proposal, augmented reality app showing real-time water quality parameter visualization in local water bodies. The content emphasizes sustainable approaches while addressing global water quality crises, with particular attention to environmental justice aspects of water pollution. Chapter 13, Climate Change Adaptation 13.1 Impact on Water Resources, Hydrologic Cycle Disruptions, Precipitation Shifts, Increased Intensity of Rainfall Events, Changing Snowmelt Timing, Earlier Peak Flows, Expansion of Arid Zones, Mediterranean, Southwest U.S., Extreme Events, Compound Flooding, Rain and Storm Surge, Megadroughts, Colorado River Basin Case Study, Water Quality Implications, Thermal Pollution, Stream Temperature Rises Affecting Ecosystems, Salinization. Coastal Aquifer Intrusion, Florida, Bangladesh, Pathogen Risks, Warmer Water Promoting Harmful Algal Blooms, Infrastructure Vulnerabilities, Design Standard Obsolescence, IDF Curves Needing Climate Adjustments, Dam Safety Concerns, Spillway Capacity Inadequacy 13.2 Adaptive Strategies, Engineering Solutions, Flexible Infrastructure, Adjustable Weirs, Multi-Purpose Flood Spaces, Rotterdam's Water Plazas, Netherlands, Supply Diversification, Stormwater Harvesting, Singapore's ABC Waters, Brackish Water Desalination, Ecosystem-Based Approaches, Watershed Restoration, Reconnecting Floodplains, Rhine River Program, Green-Gray Hybrids, Levees with Riparian Buffers, Institutional Innovations, Dynamic Governance, Adaptive Management Frameworks, Colorado River Drought Contingency Plan, Financial Instruments, Catastrophe Bonds for Water Utilities, Community Resilience, Early Warning Systems, AI-Enhanced Flood Prediction Models, Participatory Planning. Indigenous Knowledge Integration, Australia's TNCs, Chapter Features, Risk Assessment Tools, Climate Stress Testing for Water Systems, Vulnerability Mapping Workshop, Global Casebook, Success, Netherlands Delta Program, Lessons, Cape Town's Drought Response, Future Scenarios, SSPRCP Scenario Analysis Exercises, Decision-Making Under Deep Uncertainty, DMDU, Methods, Ethical Dimensions, Climate Justice in Adaptation Funding, Transboundary Water Conflicts. This chapter equips professionals with both technical tools and strategic frameworks, emphasizing no-regret measures and transformational adaptation. Would you like to expand on urban heat island interactions or include a section on carbon-neutral water utilities? New feature proposal, Interactive Climate Scenario Explorer showing localized water impacts under different warming levels. The content addresses the urgent need for proactive planning while maintaining scientific rigor and equity considerations in adaptation measures. Chapter 14, Emerging Technologies in Water Resources Engineering 14.1 Remote Sensing and GIS Applications, Advanced Monitoring Techniques, Satellite-Based Systems, NASA's GRACE for Groundwater Monitoring, Sentinel-1 for Flood Mapping, SAR Technology, Drone/UAV Applications, High-Resolution Topographic Surveys, Thermal Imaging for Leak Detection, GIS Integration, Decision Support Systems, Watershed Delineation and Land Use Change Analysis, 3D Hydraulic Modeling Integration. ArcGIS Pro and HEC-RAS, Real-Time Dashboards, Dynamic Flood Risk Visualization Tools, Case Studies, California's SGMA Implementation, using INSAR for Subsidence Monitoring, Nile Basin Initiative, Transboundary Water Data Sharing Platform 14.2 Smart Water Systems, IoT and Sensor Networks, Smart Metering, AMI, Advanced Metering Infrastructure, for real-time consumption tracking, AI-powered leak detection, like FIDO-Tech, water quality sensors, continuous TOC, total organic carbon, monitoring, digital twins, virtual replicas, Singapore's pub digital water modeling, predictive maintenance for treatment plants, blockchain applications, water rights management, Colorado River Basin pilot projects, supply chain transparency, bottled water sourcing verification. 14.3 Desalination and water reuse, next-gen desalination, energy innovations, wave-powered desalination, Onika technologies, graphene oxide membranes, brine management, mineral extraction from concentrate, water reuse breakthroughs, direct potable reuse, DPR, Orange County's GWRS expansion, cloud-based pathogen monitoring, industrial symbiosis, brewery wastewater for urban farming, emerging alternatives, atmospheric water generation, hydro panels, source water, in arid regions, bio-inspired solutions, fog harvesting biomimicry. Chapter features, technology comparison tables, cost-benefit analysis of desalination methods, sensor technology. Specifications, hands-on modules, QGIS tutorial for floodplain mapping, Python script for IoT data analysis, future trends discussion, quantum computing for water optimization, space-based water resource management, ethical considerations, digital divide in smart water adoption, energy water nexus challenges. This forward-looking chapter bridges cutting-edge innovation with practical implementation, featuring 45% real-world case studies and 30% hands-on technical content. Would you like to add a startup spotlight section or include an expert interview on AI regulation? New feature proposal, virtual reality tour of a digital twin water treatment plant. The content prepares engineers for Industry 4.0 challenges while maintaining focus on sustainable development goals and climate resilience. Appendices. Appendix A, unit conversions, length/distance, 1 foot equals 0.3048 meters, 1 mile equals 1.609 kilometers, flow rate, 1 CFS, foot superscript 3/s, equals 0.0283 m superscript 3/s, 1 mgd equals 3.785 mld, million liters per day, pressure/head, 1 psi equals 2.31 feet of water head, 1 bar equals 10.197 meters of water column, area/volume, 1 acre equals 0.4047 hectares, 1 acre-foot equals 1,233 cubic meters. Appendix B, hydrologic and hydraulic formulas, Manning's equation, \v equals \frac 1 nr 2/3 s1/2 Darcy-Weisbach head loss, \h_f equals f \frac ld \frac v2 2 grams rational method, peak flow \q equals c \i Thies equation, well hydraulics \s equals \frac q4 pi tw, u, appendix c, case studies 1. 3 Gorges Dam, China, hydropower benefits versus sedimentation challenges, relocation impact on communities. 2. Aral Sea disaster, Central Asia, irrigation-induced shrinkage, ongoing restoration efforts. 3. Singapore's NE Water Program, public acceptance of recycled water, membrane technology advancements. 4. Cape Town's Day Zero crisis, demand management strategies, climate adaptation lessons. 5. Los Angeles spreading grounds, managed aquifer recharge success, stormwater capture innovations. Appendix features, quick reference tables, material roughness coefficients, Manning's N, unit hydrograph conversion factors, equation derivations, step-by-step proofs for key formulas, interactive elements, digital version, unit conversion calculator, formula rearrangement practice tool, expanded case metadata, technical reports and primary data sources, interview links with project engineers. Would you like to add a glossary of terms or include sample calculation worksheets? These appendices are designed as both field reference tools and teaching supplements, with direct relevance to all preceding chapters. New feature suggestion, augmented reality overlay showing real-time unit conversions when scanning engineering drawings. The appendices transform theoretical knowledge into practical, actionable resources, completing the book's utility as both academic text and professional handbook.